Well, good evening. We are talking about polar coordinates out and around. This is a fun session tonight we're going to have. I'm joined once again by Vicky Carter, Steve Kokoska, and Tom Dick. Really excited to have you all here sharing your expertise with these students and teachers. My name's Curtis Brown, and this is Pre-Calculus Live. Uh, just a couple of housekeeping things before we jump into the content. We are going to have a certificate for teachers that if you guys want to get some professional development hours, you can email me for that. I'll put my email in the chat here in just a little while. And then secondly, if you are following along and wanting to try to do some of the problems with Steve and Tom and Vicky, the problem set is down in the description of this video. You can download that and follow along. And then tomorrow, sometime after the live stream, we will have the solutions document up there for you to use with students. Yes, students, I don't post the solutions document before the live stream because we don't want you guys to have the solutions until after we've made the video. All right. I think I'm turning it over to Tom. Is that right?
Correct.
Sounds good.
All
All
right.
right.
Take it away, Tom.
Okay. I'll get on my screen, and what I'm going to do is just start out uh, looking at some basics of polar functionality on the TI-84. And so this is just kind of the nuts and bolts. And I've opened up my TI-84. Hopefully you can see it there. And what I've opened up to is the Y equals screen. And when you're plotting functions in pre-calculus, I mean, over 90% of your time is going to be spent with the Y equals functionality. But when we get to polars, we're going to want to be able to change and be able to do polar graphs. And there's really some pretty neat functionality here. So what I'm going to do is hit the mode key. And if we take a look down here on that fifth line, you see function in bold there. Let's scroll down there or arrow down and move over to polar. And when we do that, when we go back to the Y equals menu, it looks quite a bit different. Now we've got R1, R2, R3. These are the radius function as a function of, well, there's a new independent variable. It's theta, which is that directed angle measured from the positive x-axis. And in fact, your xt theta n key, once you're in polar mode, it's automatically a theta key. In fact, I'm just going to hit that key. And there you can see a nice theta. And by the way, even if you're not in that mode, if you want to get a theta symbol for some reason or other, it's way down here. It's the alpha shift of 3. If you can see that theta down there on the alpha shift of 3. Anyways, what else is different? Well, let's take a look at the window. Oh, okay. Well, I see X min, X max, Y min, Y max. I'm used to seeing those. But I've now also got a theta min, a theta max, and a theta step. And so we've got both X and Y as terms of our rectangular coordinates, but we're also dealing with R and theta is our independent variable. Theta min is 0. Okay, theta max, 6.28. That looks kind of familiar. Looks suspiciously like a decimal approximation for 2 pi. But this theta step looks a little bit weird. 0.130899. Not sure what that is. Tell you what, if you can kind of keep that in mind, 0.13089. Let me quit out of that window, and I'm just going to calculate pi divided by 24. Looks familiar. That's what the theta step is. What they've done is they've defaulted to a step value that, if you think about it, if you take multiples of pi over 24, you're going to naturally hit 4 pi over 24. That's pi over 6. 6 pi over 24 is pi over 4. 8 pi over 24, that's pi over 3. You're going to hit all your nice multiples, rational multiples of pi. And so that's been kind of optimized for that. Okay. Um, just for grins, why don't we go ahead and graph this function? It's a weird function. I think actually Steve may look at it a little bit later on too. This R is just equal to theta. I'm going to just go ahead and hit a zoom decimal window, see what we get. Oh, interesting. It's a spiral. What's happening here is, well, when theta is 0, we're pointing along the positive x-axis. We have a radius of 0. And as we move around, as theta increases, the radius is increasing too. Instead of me wagging my tongue, why don't I turn on the trace? And there's two kinds of traces here. I think I have the one that's set up for polar. So notice that as I trace on this with my right arrow key, it's now advancing the value of theta. And with this particular function, the R value is always equal to the theta value. Here I am at theta 1.57. Okay, that must be pi over 2 or very close to it. And so I'm up at, if I take in XY coordinates, that's 0 and 1.57. Okay. If you want, if you go to format, if instead of polar graph coordinates, you can change over to rectangular graph coordinates. And in fact, I think that's the default. So when you go from y equals to polar, you may want to change this to the polar graph coordinates. If I go to rectangular graph coordinates and go back to my graph and trace again, notice what I'm seeing now is I'm still seeing my theta value, but now it's giving me the coordinates of that point in terms of x and y. Okay. All right. And so that's kind of the basics for graphing. Let's see what else might change here. We could go to a table. And the table is, instead of x and y1, we have theta and r1. I've got this, let's see if I look at my table set, you could set it up, table start, delta table, might want to set that to pi over 24. Let's go ahead and give that a shot. And put it on auto. Go back to the table. And this was not a real exciting function in terms of, since the R is just equal to the theta. But you can see these are the decimal approximations. And let's see, this one here should be approximately pi over 4. And then down here, we've got pi over 6, pi over 3, and so forth. So I think that is the basics. Let me show you one of the things when you're just introducing polar coordinates, something you may want to try and do. And when I turn this over to Steve, I'll steal a little bit of his thunder, but just look at the very first problem he has is just looking at plotting points that are in polar coordinate form. And the polar coordinate form is the radius, r, and the angle theta. Those are your two coordinates. The first one he has is r is equal to 2, and the theta is 5 pi over 6. Well, here's a nice way you can locate that on the 84. I'm just going to plot r1 equals to 2. Let's graph that. Just a circle of radius 2. If I turn on the trace, and I could now ask for a particular theta value. So I'm going to go ahead and put in 5 times pi divided by 6. And that should locate that point on that circle. There it is. And we can kind of do a visual. Does this make sense? Let's see. This is 0. Pi over 2 would be pointing along the positive y-axis. A pi would be all the way over to the negative x-axis. So 5 pi over 6 looks about right. And here are my X and Y coordinates for that point. Okay. So that's kind of a nice way to just using plotting a circle and then asking for a particular theta value where you can locate points that are in polar coordinates and see where those are going to be at in your rectangle.
Cool.
Okay.
Tom, before you leave
Yeah, I was
that,
going to pause there to see if you or Vicky had anything you
I
wanted
have
me to.
one question.
Sure.
Maybe you or Ricky can help. Can you go to the window key just for a minute?
Sure.
Okay, so on theta step, I think I understand why the calculator defaults to pi over 24. Then it's sampling at common angles. I get that. Is there an advantage or disadvantage to making that theta step even smaller? Like what if I made it 0.05? Does that inhibit the graph in any way? Would it possibly give me a bad graph, an unconnected graph? Is there any advantage to that?
There's no obvious disadvantage that I can think of other than the smaller that step size is. For
Yes,
one, the plus will be more precision.
yes,
We're basically plotting more points,
okay,
and you'll have a finer trace.
okay,
The downside is the more points you plot, the slower the plot will be. But I'm not sure that's how big of an issue that is. So,
okay.
for example, I'm going to let's make it 0.05. So that's a little less than half the step size before. So that's twice, more than twice as fine. Okay,
Okay,
twice.
You
yep,
could just do pi by 48. That way
Could
you
do
still
that,
hit the
yeah.
nice
So
number.
if we
okay,
want to do exactly half, so we're still getting those nice multiples.
yes,
Do pi divided by 48 or even 72,
okay,
something like that.
okay,
Go ahead and graph. And
And
now when
slow.
I trace the theta values, you can see that's a much smaller increment.
yes,
And in fact, I'm not sure I even paused long enough on the window. When I did pi over 72, it went ahead and calculated what that approximately is in decimal. So we can see it's about a third of what we had before, right? Pi over
yeah,
20, pi over 72.
Yeah, and then another thing to think about is you're our own computer. So I would
Yes,
like to experiment. It could really slow down a handheld a little bit. So it might be something that, they may want to play with it to see how much it does affect the graphing on the handheld.
definitely a trade-off in terms of more
Hmm.
precision, but taking more time to graph. Yeah.
So if I were to pick a larger number, but not a multiple of pi, so not pi over 24, not pi over 12 or pi over 6, but zero point 0.5,
About one.
even better. What happens there?
You might be surprised.
Okay. How about that? I
Jumping
was,
in pretty big chunks.
yeah, I was
It's
wondering about,
connecting those individual dots. So if I turned on the
Steve,
trace,
did you
it would be
predict
jumping
that would
by.
happen?
I did. I was wondering, I was more concerned about what was happening at the very end of the graph. So going from 0 to 2 pi. So I think in a case like this, you're not seeing the connected graph.
Right, because you got to 6 because I was going whole integer multiples there.
Yep,
So the next value is beyond theta max.
6.28.
So 7's too big, so that's where it stopped.
Yep.
So if I wanted this to be a really nice polygon, what I'd want to do is maybe do something like, I could still make a polygon, but I could put in
Yes,
something like pi over 6 or pi
yes,
over 3. Let me do that.
yeah, sure.
And now that should, I think, give me like a hexagon. Let's see.
How
Yeah, there
about
it
that?
is.
That's
Bingo.
kind of cool.
And it's kind of a cool way to plot polygons is
Sure,
by basically choosing your central angle and
sure.
plot it very nicely. So
Cool, Tom. Thanks.
I was
Sorry about that.
just gonna say, Tom, you hit on a nice little geometry topic there to be able to
yeah,
draw those polygons that way and make use of it.
yeah.
Uh, talk about how talk about those polygons and ways to kind of play with that. I know it's not a pre-cal topic necessarily, but it's kind of a cool use of it.
And when you get right down to it, when we do plot a circle, like we had before, so let me go ahead and put it back to pi over 24.
Yes.
If I really think about it, this thing looks like a circle, but what I've really plotted is a polygon with lots and lots and lots of sides. So many sides, it looks like a circle. So we're getting at some limits perhaps. Okay. All right. So I think what I'll do is stop the share and turn it back over to you, Steve.
Okay.
Go ahead.
All right. Thanks, Tom. That was cool. All right. So we've got some cool problems tonight that deal with polar coordinates. And I'm going to start out by simply trying to plot some of these points whose polar coordinates are given. I wrote off to the side here that these polar coordinates are given in the form of r and theta. And Tom, you may remember this. One of the conferences that you and I were at recently, I believe somebody was arguing with us about polar coordinates should be given in the form of theta r, because it's always theta that we plot first, like in an XY coordinate system. Why don't they write this as theta r? And I don't have an answer for that one, but maybe there's something historical as to why we always write this as r theta. But anyway, something to think
Is
about.
that true that you always plot the angle first? You move the angle and then go out r?
Well, that's the way I do it. I think that's the way most people do it, Curtis. I don't know. How do you do it?
Well,
You didn't
I
do
tend to,
okay,
if I'm plotting a single point, if I'm plotting a single point, I figure out r and then I sweep the angle. I know
okay.
that's bizarre, but
Well, I would argue that that might make it more difficult if r were negative.
oh, for sure it does.
Okay.
But it's how my mind works.
Okay. Explains a lot. Okay, here we go. Let's try a couple things.
Explains a lot. Thanks. Thanks.
All right, so I'm plotting these rather than in an XY coordinate system. I've actually drawn this polar grid. And so I think of this as the origin right here, and this line going out along the positive x-axis is our polar axis. And so the way that I would plot a point like this is I would draw this angle measured counterclockwise from the polar axis. So that's 5 pi over 6. And now what I'm going to do is draw a ray from the origin, measuring that or indicating that angle. So I'm going to draw this line here. And because r is positive, I'm going to go out 2 units from the origin. And there's the point. So I draw the angle measured counterclockwise from the polar axis. I draw a line segment from the pole, from the origin, indicating that angle. It's kind of the terminal line for that angle. And then if r is positive, I know that my point is along that line. So I'll try to hit all 4 possibilities here. I tried to do that anyway. Let's take a look at this one down at the bottom. So this is minus 1 pi over 4. So the very first thing I did is I drew this, measured this angle, pi over 4, and drew a line out to indicate the terminal point for that angle, a terminal line to that angle. But wait, r is negative, so that means I have to draw this other line here, 180 degrees from that, the other direction, and I go out 1 unit along this line, and there's minus 1 pi over 4. Can you see that dot there? There it is, right there. So I drew the angle pi over 4. I drew the line indicating, measuring that angle, but r is negative. So I've got to go 180 degrees or pi degrees over here in the other direction, opposite direction. And my point minus 1 pi over 4 is over there, sort of in the third quadrant. Here's another one. Well, this time the angle is negative, negative 2 pi over 3. That's okay. I still measured that from this polar axis. This direction is considered positive. So I go minus 2 pi over 3, draw that line, that kind of what I think of as a terminal line from the from the origin. R is positive, so I go 3 units out from the origin, and there's the point 3 minus 2 pi over 3. Hey, pretty cool. This is working. All right, let's try one more. We've got 2 negatives in there. So this time the angle is minus pi over 6. All right, so minus angle and negative angle is measured there. There's the negative pi over 6. I can draw my line indicating that terminal line, indicating that angle, minus pi over 6. But wait, r is negative, so I have to draw this line in the opposite direction, and I have to go 2 units out along that line because r is negative, and there's the point minus 2, minus pi over 6. Cool. I kind of like those polar grids. They're kind of neat to draw. I think, Tom, you may show us a little bit of that with the TI-Nspire. I've drawn these with Mathematica, which is kind of cool. And you can put in the common angles, and you can actually put in as many angles as you want. Kind of cool.
So Steve, before you leave that one,
Yeah, sure.
note
Go ahead.
that this is actually the same point as the first point that we graphed. And so these ordered pairs are not unique. And that's something very important for our students to know about polar coordinates. So there are infinitely many ways we could actually give coordinates for that point.
Yeah, thanks, Vicki. And one thing Tom touched on that I was going to put in here is this point where r is 0 in any angle. Let's put a pi over 4. Where r is 0 in any angle in there, what point is that?
Nobody's responded.
Okay, we'll leave that as an open question for now.
The origin, Steve.
Very good. Excellent. Tom, should I
Even I know that one.
Okay, okay. Should I continue with 2, Tom?
Yeah, go ahead, Steve.
Okay, all right, thanks. Okay, so for 2, what we're going to do is convert some polar coordinates to rectangular coordinates. So I'm just going to remind myself over here how I'm going to do that, how I'm going to get from polar coordinates to rectangular coordinates. Remember, these formulas are x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. So at least in my mind, this is pretty prescriptive. I'm just going to recognize what r and theta are up here in this ordered pair, and I'm going to plug them into these formulas. So, okay, x is equal to r cosine of theta. All right, I have to think a little bit about, well, what's the cosine of 5 pi over 3? Let's see, that's a common angle. Let's see, where is that? Over in the 4th quadrant. So let's see, that first point, pardon me, the x coordinate there is 1/2. Yep, that's right. So there's the x coordinate, square root of 2 over 2. Y is r times the sine of theta. Okay, so the sine of theta is minus square root of 3 over 2. And I think I did a little bit of simplification or rewrote that a little bit differently. I think I've got that right, minus the square root of 3 over 2. Now, I didn't do this, but one might plot that polar coordinate like we did a minute or two ago, and just make sure, as Tom talks about, just make sure that this makes sense, that the XY coordinates do seem to agree here with that polar coordinate. Let's try another one. All right, same thing. X is equal to r times the cosine of theta. R is negative this time. Cosine of a minus pi over 6. Let's see, where is that? Minus pi over 6 here down in the 4th quadrant. Let's see, I've got to go way out there. So that's a square root of 3 over 2. Yep, I believe that. The 2's cancel. Minus square root of 3. Y is equal to r times the sine of theta. Sine of theta, in this case, sine of minus pi over 6 is a minus 1/2. Little simplification, that's 1. So the Cartesian coordinates, the xy coordinates, are minus square root of 3 and 1. So pretty straightforward using these formulas. Vicki, do you anticipate that there would be any questions like this on the exam, perhaps in the multiple choice portion?
In the multiple choice portion. So while we're talking about that, let me just mention there is nothing about polar coordinates in the free response question because they are task models that are very prescriptive about what is going to be asked, and polar coordinates are not included. So they are going to be multiple choice questions.
Okay. Thanks, Vic.
Hmm.
All right.
What
Well, Vic,
go back to that one just a minute, Steve. I was
sure.
just gonna give the
There you go.
students that are online tonight a hint. Um, One thing to kind of think about too is, and you mentioned it, but I want to say it maybe a little bit differently. Think about where the polar point is located by practicing the skills that Steve just went over a few minutes ago, and then see if the signs of your rectangular coordinates match for the quadrant that you realize you should be in, because that's a good way to check that you've taken the correct sine or cosine values of those angles that you've been given.
Uh,
I agree.
I just got a question in the chat. Is Y correct? I haven't thought through your solution, but is your I guess in number 2B, is the solution for Y correct? A +1?
Well, let's look at it with polar coordinates. How about that? See if it seems to agree there. What do you think about that? So minus
I think
pi,
that's a great idea.
so minus pi over 6 is right here.
Oh, sorry. I'm looking at the chat. That means number 2A, number 2A, not number 2B. Apologize.
Yeah, I think that's right.
Yeah, I imagine most of the students would probably write negative square root of 6 over 2,
Yep,
which could be also written as the square root of 3/2
yep.
or
Right, the
negative.
square root of 3/2. That's what
Yep.
I thought that makes sense. I just wanted to make sure we got that clarification in there.
Yeah.
But yes, graphing is the right gut check too. And making sure saw this in the chat there. All right,
And
thank you.
Vicky and Tom, correct me if I'm wrong too. Sometimes what students have to do is to manipulate their answer a little bit to make sure that it fits one of the four possible choices,
Yep.
correct?
Yes.
So you may not see it in the first simplification or the first way that you write the answer, and you may have to do some other manipulation. So yeah, good question. Okay, let's try 3 here if we can. So this time, let's go the other way around. Let's see if we can convert some rectangular coordinates to polar coordinates. Let me see if I can arrow up just a little bit. And so the way that we do this is by using these equations. We know that x squared plus y squared has got to be equal to r squared. And we know that the tangent of theta has got to be equal to y divided by x. Okay, now we've got to think a little carefully. I actually think that 3B is probably the hardest problem we'll do tonight. I think you have to think carefully here about where this xy coordinate, where this point is actually located. And you have to make sure that you do indeed choose the correct angle theta here in finding or in satisfying tangent of theta is equal to y divided by x. Okay, I'm just going to sneak off to the side, do a little bit of scribbling here. Here's an xy axis, 2 square roots of 3. Well, that's about here. I'm in the first quadrant. So I'm going to keep that in mind here as I go to find r and as I find theta. So let's see, r has got to be the square root of x squared plus y squared. Let's see if I did that right. That's 4. 4 times 3, 12, square root of 16. So that's 4. And the tangent of theta has got to be y divided by x, the square root of 3. So, okay, can I come up with an angle theta here that, all right, is going to be in the first quadrant, whose tangent is the square root of 3. And I think that's a common angle. So that's got to be a pi over 3. So that means that the point is represented by 4 pi over 3 in polar coordinates. One thing Vicky said a minute ago, these points are not unique in polar coordinates. So there are other ways that I could write that. I think I remember a worksheet or seeing a worksheet or two where, okay, here's a point in polar coordinates, write 4 or 5 other ways that you can represent this. So that's good practice, I think. B, don't let me make a mistake on this one, guys. -1, 2. I'm going to do the same sort of thing to help me a little bit. Let's see, -1, 2. Here we are. That's a point down here in the third quadrant. I want to make sure that I end up with an angle theta here that puts me in the third quadrant there. Okay, so R has got to be the square root of x squared plus y squared. Did I do that right? 1 plus 4, that's got to be the square root of 5. Here's where the issue is, I think. Tangent of theta is y divided by x has got to be a -2. Theta has got to be equal to the tangent inverse of -2. I got to think about this just a little bit. Let's see. What sort of a value does the tangent inverse return? Vicky, do we know about in pre-calculus, AP pre-calculus? Do we know about that
Yes.
range? Okay,
Yes, that range of -pi/2 to +pi/2.
beautiful. So
And the,
minus
and
one.
and it is a topic that is just a few topics removed from when they get to the polar work. So they would have just covered it.
Okay. So I think that returns an angle over here. I think over there in the fourth quadrant. And so to get the angle that I want, let's see, I added pi and now I'm questioning that. Is
Yeah.
that right?
No.
I think what I want to do is take pi minus that. I want to get over to here into this angle right over here. So here's the angle. So I want to take pi minus that. So we'll fix that a little bit. So good question. I got to think a little bit about that. I got to think about where is that angle located. I got to make sure that I'm in the right quadrant. I got to think about what the tangent inverse really returns. And I think there's my point in polar coordinates.
So,
Fantastic.
so Steve, another way that students might want to think about this is start the way you did, definitely by thinking about that point,
Yes.
-1, 2 being in the third quadrant, but maybe realizing that inverse tangent of +2 would put us in the first quadrant, and then we could add pi, and that would be an equivalent that would
I like
work.
that. That's even a better way to think about it. Yeah, I like that.
So
So
they,
here's another
they
way we could write that.
so the students are going to have to be very careful about these utilizing inverse tangent, but it's necessary here because we don't know, it's not a common value. We don't know an inverse tangent for 2 or
Yeah.
-2 like we did in the first question.
Makes a nice multiple choice question, doesn't it?
Mm-hmm.
Say, Steve, wouldn't this be in the
I,
second quadrant?
I'm really glad, Tom, you said that. I was looking at this and thinking the same
Oh,
thing. And
it
so
is.
is
Oh, you put
Stephen
it in
Beck.
the third
I
quadrant.
put it in the third quadrant. I saw it. This is a small mind.
So we were all on the same page along with Stephen Beck. So
I'm
yeah.
erasing all of that. I was right.
You were right all along. No, you weren't, but
Thanks,
Just
Phil.
wait till we do Monday night calculus on April Fool's Day.
We're going to do something there for sure. Thank you. Okay, good. Very good. All right, let's try another one. Let me know when you want to come in with technology, Tom, okay?
Okay.
All right, I did this one in kind of a different way too, Vicky. I don't know, you may have another way of looking at this one. I want to express this complex number, 1 minus I, in this polar form, r cosine theta plus I, r sine theta. All right, so the way that I thought about this is the complex number has rectangular coordinates. Did I get that right? 1 minus 1. So I'm going to go back and think about this like I did on the previous page. And I've got r equal to the square root of x squared plus y squared. I think I did that right. That's the square root of 2. And now here we go again. I want tangent of theta to be equal to y divided by x. So that's going to be a -1. So I think that tells me that theta is equal to minus pi over 4. So here's a way I think I can represent that. And then I wrote it another way too. I don't know if this would be acceptable or not on the exam. So this is r times the cosine of theta plus I times r times the sine of theta. Some of us don't like those negative angles in there. So I think a way that I could simplify this is recognizing that the cosine is an even function. So the cosine of minus pi over 4 is the same as the cosine of pi over 4. And the sine is an odd function. So I can bring that minus sign all the way through the sine and all the way out in front here. And there's another way that I can write it. So that's kind of cool. I think there's even another way I could write that with theta equal to 7 pi over 4.
Yes, and that this is back to if it's a multiple choice question, they're just gonna have to think about the multiple possibilities that
Yeah.
they could have there and
Yep.
work it and then think, well, is one of these an equivalent to that?
Yeah. Yeah. Cool. Okay, let's get to graphing some of these. And Tom, I suspect this
So
is you may want to come in.
yeah, it would be okay if I came in here for just a
Perfect. Perfect. Okay. There you go. All yours.
okay. Um, just wanted to go back to the 84 briefly and discuss this converting between coordinate systems, how
Okay.
that might look on the 84. And
Okay.
so what I'm going to do is actually go to the mode and look down further than the function parametric 4. Keep going down until I get to this row that has real
Uh-huh.
and a plus bi. That's a complex number form. But there's a second complex number form that's related to the one you just did. That
Mm-hmm.
says r e to the theta I. That's also known as a polar form, but it's written using the exponential. I think the key thing is you can still read off the r and the theta from this form. And I just wanted to kind of demonstrate what that would look like.
Okay.
I'm going to change that to re to the I theta. Then I'm going to go back to the calculator screen and I'm going to enter in the complex number that you just entered in.
Okay.
1 minus I. Now we need that lowercase I that is the imaginary square root of -1. That's
Mhm.
found down here on the this second shift of the decimal point. So if you
Got it.
look down here, you might be able to see that I. There we go. Looks good. Now I'm just going to enter that. And the coefficient here in front of the exponential, that's the R. And if you look at that, if we can, it's recent enough in our memory. I think you had square root of 2.
Yes, sir.
1.41. That's looking good.
Yep.
And let's look up here in the exponent. We're now looking for the coefficient of I in that exponent. And that should be our theta value. And so folks can take a look at that and see, well, what theta value did they use? Did they use like a negative pi over 4 or 7 pi? What did they use? And they did use, I think, a negative pi over 4 here. And we could actually kind of double check. Let's just go ahead and calculate negative pi over 4. Yeah, that's exactly what it was. Okay.
How about that?
And in fact, I think what's kind of interesting is back on your number 3, where you were given numbers in rectangular coordinates, unless Curtis knows some other way or Vicky, this is the way to do it, is you actually change them to complex form while you're in this re to the I theta I format. And then you can read off the radius and uh, angle. So for
Mhm.
example, I think you had one that was like negative 1 comma 2. Well, I would enter that as -1 plus 2 times I.
Okay.
Boom. Now it's giving me the radius and the angle theta. I can read off of that. Now, trying to figure out what those were, you did it very nicely with some nice multiples of pi for your angle. This is probably some radical form. I'm trying to remember. Was ended up being square root of 5 or something like
Yeah.
that. Yeah. But that's a way you could do this conversion. So it's just a little bit of a kind of interesting thing you need to do, but it brings you into the complex numbers with that. So, by the way, just an anecdote. If you look at this exponential polar form, if you had a radius of 1 and an angle of pi, let's see, that would be, I think it ends up being equivalent to, let's see, -1.
Yeah.
Yeah.
Yeah. So Steve and I were at the University of New Hampshire together many moons ago. And there was that's an agricultural school. It's a land grant college, and they had this big barn right outside the math department building that somebody had painted on there e to the pi I plus 1 equals 0. So you could see it by airplane. So
Oh my goodness.
all right, I'll stop on that note and turn it back over to Steve.
All right, thanks, Tom. All right, I'm going to try to graph a couple of these polar equations, and I'm going to show you a partial table of values and how I might approach this if I had to do it by hand. I'll show you what I got when I tried to graph these using Mathematica. There might even be some names of some of these graphs. And then I think, Tom, maybe you'll show us how to graph these using technology. Is that correct?
Yes, sir.
Okay. So this first one is r is equal to 1 plus the cosine of theta. Let me ask before I go through this, Vicki, our AP pre-calculus students expected to know some of the common polar graphs?
They do not have to know them by name, but they definitely need experience with what we as teachers traditionally call some of the classical curves that you get with polar coordinates.
Okay.
I definitely name drop in my classroom as I
Okay.
did them, but again, we're not going to say, you know, which of these is the graph of a cardioid, for instance. They just need to be able to, having been given, so again, it's going to be a multiple choice question. They'll either have a graph and have to pick out the function, the polar function from 4 choices, or vice versa. Give them a function and they'll have 4 graphs to pick from.
Gotcha.
That's basically what's going to happen with those.
Okay. Vicki, may I ask if they had a question like that and the graphs are presented, would they be given in an XY coordinate system or in a polar grid like this, do you think?
The one that immediately comes to mind, it was in a polar grid.
Was okay. Okay. So like this.
Yes.
Cool. Okay. All right. So what I did is I picked some common angles. I think that's the best way to start. And I went 0 to pi. And after I graphed those points, I sort of dawned on me, oh, yeah, I know what kind of a graph this is. And I was able to complete it. I know there's some symmetry here. I just want to make sure that some of these points make sense. The first one has R2 theta 0. So that means the angle is 0, but I'm out here a distance of 2 units from the origin. The next one is pi over 6. So here's my angle, a common angle, pi over 6. And I'm out a radius or a distance of 1 plus the square root of 3 over 2 from the origin right there. So these values seem to be getting a little bit less as I get to pi over 2 and beyond. So I plotted these points and I connected the dots here. And okay, I did this with a little bit of technology. And I think Vicki name dropped a minute ago. I think this is a cardioid, isn't it? This is
Yes.
a cardioid. I want to pause there for 1 second because I think one of you, Tom or Vicki, mentioned a way to graph these by looking at a plot in the XY plane. Did you
Yeah,
want to talk about?
I think that might be what Tom's got up his sleeve to show next.
Okay.
And
Shall I
I
go?
and I think it'll be clearer if with the technology, and we might can come back to it perhaps.
Should I continue, Tom, or would you like to show that now?
Um, I I could go ahead and show it now. That might be
Yeah.
good.
Okay.
Okay, thanks.
Okay.
Okay. So I'm going to actually switch over to the TI-Nspire. And, you know, I know that lots and lots of our pre-calculus classrooms out there, it's probably going to be the TI-84 is going to be a more common device that's being used by students. But I would encourage teachers, even if you're using the TI-84 in your class, to think about possibly getting the TI-Nspire software, just because there are some good documents that you could use for illustrations and getting points across in class. And so there's a lot of different um, documents out there that are pre-made. You don't have to reinvent the wheel. And in fact, Steve and I have made a few of these using Nspire. For example, this one's a polar graph grid, just to show you what this looks like. And basically what we did is go ahead and put polar graph paper onto the Nspire. And so now you can basically have a couple of sliders here that control the radius and control the angle. And you can see that the angles in both radian and degree mode down here, but radian's going to be the mode to be in for the recalculus. And so one can also graph on that polar grid. And here's that spiral again. And again, we can use this little slider to trace. But you can see it help with the polar grid. It kind of helps you visualize exactly where you're at there. Now, Vicki had recently shared a document with me that was, I think, created by Steve Phelps.
Yes.
And I tweaked it a little bit, but I thought it was really, really cool. And so with him, thanks to him, it was a way to, I mean, these polar expressions where you see an R of theta, we really should think that that is another kind of function. Okay, the independent variable is theta, the dependent variable is R, just like a y equals f of x. And what Steve Phelps put together here was a document where he actually took the same expression in theta, R equals an expression in theta, and changed it to y equals the same expression in terms of x. So you can compare the two. So here's an example of the one we just did, or Steve just did, Steve Kokoska. This is that cardioid, and this is the R equals cosine theta plus 1. But over here is y equals cosine x plus 1. So we can see what it looks like y as a function of x and r as a function of theta for that same expression. And I've got a clicker here where it's advancing both the x and the y. Excuse me, both the x and the theta. And you can see, so the brown here is giving me the value of x and the value of theta. The green is the dependent variable. Over here, it's a length of that vertical segment is going to be y, and this is that radial segment. So kind of cool. Now, he's got a pretty small increment on this slider. He's also got it where I could just grab this point and move it. Notice it's coordinated. When I move it on the rectangular function graph, it also changes over here. So I thought that was really cool. It really kind of brings home what the graph of a function looks like is really going to depend on your coordinate system and what kind of frequency. So we can take the exact same expression when we graph it in polar coordinates, we get this interesting shapes like a cardioid. And over here, we're getting a kind of a sinusoidal graph. See, Vicki, I don't know if you wanted to, because I know you used this file in a recent webinar you did. If there's anything
Yes.
you wanted to point out.
No, I mean the connection I think is so important, and I know some teachers are actually, instead of starting with trying to sketch the polar graph first, they sketch the rectangular graph, and then the features of that rectangular graph is what helps the students then form the polar graph. And I think back, like when I was learning this eons ago, why didn't we do that? But there was no beautiful technology that helped us visualize these connections. And so I guess it was just too much it's too much trouble to look at it that way, or you know, whatever. But I think it's very important for the students to see that connection.
So Vicky, would
go
you,
ahead.
Vic, would you encourage students, just because it might be easier, to construct the graph on the right-hand side where y is a function of x?
As
And then,
long as it's a fairly simple, and I would think most of these are fairly simple graph to draw, then yes.
so from that graph, can you go to the one on the left in some way easily?
You mean to get the graph on the left from the graph on the right?
Yes, I mean, this is a
Yeah,
nice visualization and I get it, but can you go from the one on the right to the left easily?
I think once they've had a little bit of practice with it, yes.
Yeah, okay.
Because obviously when that point is tangent at pi to the x-axis, when we have a 0 radius, then that is a strong connection to where that pointy place and the cardioid is going to occur. And instead of having to think about symmetries and things like that, I think this is a stronger connection. And I'm talking about symmetries with polar graphs. And some teachers do teach it that way. You know, look to
Uh-huh.
see is it, you know, what kind of symmetries it would have. But I see the connection, me anyway, I'm a very visual learner. I see the connection much easier when I see the rectangular graph.
Okay.
For example, I'm seeing here on the right graph, my y value at x equals 0 is 2. Over here, my radial value for theta equals 0 is 2.
Mhm.
Also, this is a maximum value for my y. This is a maximum radial value, that cardioid. And if I move this point over to, say, pi, x equal pi, I should say. Almost got it. Pretty close. Notice it's wrapped around pi over here. And my y value is very close to 0. And my radial value is very close to 0. So I think there's some really nice direct connections you can make, Steve, between these two graphs.
Yeah.
What's going on. And very neat. Now, this particular graph doesn't take on negative values, but if it did, and I think there's some later ones in this same document, of course, that's going to invert your radius through the origin, or reflect it, I should say, just like we normally do. All right, I'll turn it back over to you, Steve.
Okay. Very cool. All right, I got a couple more graphs here, I think. Beautiful. Let's try this one. R is equal to 3 times the sine of 2 theta. So I think, Vicky, another sort of common polar graph that students should know about. Maybe R is equal to a constant times the sine of, I'll say, n theta, what that might look like. I did the same sort of thing. I created a table of values over on the left-hand side from 0 to pi using some common angles. And I sketched them over here. So let's see, at 0, I'm at the origin. At pi over 6, I'm in this polar grid. So for me, that's a little easier to see. There's the angle right here, and the radius is positive. Let's see, 3 square roots of 3 over 2, right about there. As I continue here, pi over 4, pi over 3. And now I seem to be back down here at the origin when theta is equal to pi over 2. This one's kind of interesting. Now, as theta is 2 pi over 3, actually over here, notice that the radius is negative, or r is negative. So as Tom says, we're reflected across that pole, across the origin. That point is down here. So I guess sometimes, I mean, I might put in little arrows to represent this motion, or the way that this graph would be drawn as theta increases. So it starts out this way, comes back down here, this way, over here. I think it curls over here, back up, and finally down and back to the origin. How about that? So what do we call this one, Vicky? A four-leaf rose? Yeah, is that
A
right?
rose.
A rose? A rose. How about that? That's cool. Good.
Okay, I am gonna throw something in that I like to talk about with,
Okay.
especially with the roses, because I think it helps students visualize what's going on.
Okay.
If you've ever if they've ever played with a spirograph, they've made roses. They've just made some that are much more complicated than what we've done. But I think when students, if they, and I used to let mine just have a few minutes playtime with the spirograph. I had several sets, but they get that idea of that rotation, and it kind of helps them now, like with the arrows that you just put on there. It makes sense that this is how it rotates around, not only because of the values that we have, but because that's how a circle rotates inside another circle. As a lot of interesting things that can be talked about then.
Gee, you know what a spirograph is, huh, Vicky? How about that, huh? How many, how many, how many students know what a spirograph
They still sell them.
Oh yeah, I know what a
is?
spirograph is.
Okay. All right. I think I've got one more here. This one we've looked at several times already. This is R is equal to theta. This is kind of a spiral. And of course, as theta increases without bound, this spiral just keeps getting bigger and bigger and bigger. Somebody posted, I think I saw this recently, either in the Facebook group or somewhere on the web recently associated with calculus, that this sort of resembles a common shell that we see down here in Florida, right? The spiral type graph. That's kind of cool that we see that actually in nature. All right, and one more here I think we can end with. Let's look at this polar function. R of theta is cosine of theta over 2. This is kind of a neat graph. So I won't go through all the details on this one. I've graphed this using technology, but I could do the same thing as Vicky and Tom talked about. I could create a table of values. I could also graph this as y is equal to cosine of x over 2 and figure out this, reason out this graph. That's what it looks like. But we might see some questions like this, part B here. Find the average rate of change of R with respect to theta over this interval 0 to pi over 2. And then the next part of this is the radius increasing or decreasing over that given interval? Well, okay. First of all, the average rate of change would be R of pi over 2 minus 0, minus R of 0, divided by pi over 2 minus 0. So students should know that formula for the average rate of change over an interval. So I'm plugging in here into the formula up above, cosine of pi over 4 minus the cosine of 0. I hope I did that right. And a little bit of simplification. It's kind of that ugly looking constant. I'm not going to do anything more with that one. I don't know how they present that one to us in a multiple choice problem. But perhaps the more interesting question is the radius increasing or decreasing over the given interval? You might think about a particle or moving along this curve. Is it getting closer to the origin or farther away from the origin as theta moves through that interval 0 to pi over 2? Vicky, Tom, you may have some better ways to do this, but I just sort of reasoned this one out a little bit. I said, look, as theta increases in this interval, theta over 2 is also increasing. And I know a little bit about the nature, the characteristics of the cosine function. And that means if that argument is increasing, then the cosine is decreasing. And so that's how I argued on that one, but there may be another way to do it. And you may be even able to demonstrate this on the graph. I'm not sure. So that's all I got. Tom, Vicky, you got any more technology here? Are we good?
I think we've done a great job with
Yeah.
covering a lot of stuff.
Yeah.
Curtis,
Great job, Steve.
any lingering questions, Curtis?
I have not seen any lingering questions this evening hanging out here. So I think if you guys have got it, well, I think we are good to wrap up the session this evening. One thing, I just put my email in the chat there. So teachers, if you're looking for some professional development hours, I've got that ready there for you in the chat. And otherwise, we will look to see you guys on I forget when the April session is.
April 4th.
April 4th.
4th. Yes.
April 4th is the session for AP Pre-Calculus Pre-Calculus Live. So we'll be back here in about a month, and we'll look forward to seeing you there. Again, invite your students, make sure they have an opportunity to check out these cool problems, and we'll see you in a couple of weeks, I guess.
Very good. Thanks, Curtis. Thanks, Tom.
Thanks.
Very good.
Thanks.
All right.
Cool. That was great, guys.